Welcome, first-year engineers. I am absolutely thrilled to have you here today. We're going to completely demystify the very screens you're looking at right now by building the technology from the absolute basics. Whether you're tuning into this on a smartphone, a tablet, or some massive ultra-wide monitor, there's a hidden, vibrant world of physics and chemistry happening right in front of your eyes. So grab your notes, get comfortable, and let's uncover the incredible journey of the pixel.
Here's our roadmap for today's explainer. We'll kick things off with a quick intro to displays, then travel down the liquid crystal path. After a complete LCD walkthrough, we'll switch gears over to the LED path, pit the two against each other in a showdown, and then wrap it all up with a highly focused exam revision session to make sure you totally ace your finals. All right, let's jump straight into Section 1, Intro to Displays. Think about it. At its absolute core, a display system is really just a massive translator. It takes raw electrical signals and turns them into visible information that our human eyes can actually understand. And how does it pull this off? Well, through pixels. Every single pixel is made up of subpixels, specifically red, green, and blue, or RGB. By tweaking the intensity of these three primary colors, which perfectly correspond to specific wavelengths in the visible light spectrum, we can mix them to create pretty much any color imaginable. But here is the absolutely crucial takeaway for your engineering foundation. Displays achieve this using one of two fundamentally different philosophies. They either generate their own light entirely, or they just control an existing light source. Let's explore that second philosophy first. Moving right along to Section 2, the liquid crystal path. So what exactly is a liquid crystal? I mean, we all know the basics: solids, liquids, and gases, right? But liquid crystals are this incredibly cool intermediate state of matter. They literally have properties of both liquids and crystalline solids. To picture this intuitively, imagine a massive crowd of people flowing smoothly down a city street, moving completely freely, just like water. Yet somehow, every single person in that crowd is facing the exact same direction. That's essentially molecular order within a flowing liquid. Because of their elongated, kind of rod-like molecular shape, their optical and electrical properties actually change depending on which direction you measure them from. This directional dependence is called optical anisotropy, and let me tell you, it is the absolute magic ingredient we need for modern displays. Now, there are a few different types of liquid crystals, but for displays, we zero in on thermotropic liquid crystals, which change their phase based on temperature. We generally look at three main subclassifications. You've got Smectic, where the molecules form these very distinct parallel layers, so really high order. Then there's Cholesteric, which form this twisted helical arrangement that can actually reflect specific wavelengths. Those are fantastic for things like temperature sensors, but pay close attention to the Nematic class. In the Nematic phase, molecules are mostly aligned in the same general direction, but they don't have strict positional order. That means they can flow freely. We heavily favor the Nematic class for LCD displays. Why? Because they respond incredibly fast to an electric field, reorienting themselves rapidly and smoothly. All right, let's put this into practice in Section 3, the LCD walkthrough. Let's actually build one of these devices in our minds, looking at the complete architecture from back to front. Starting at the very back, you absolutely need a backlight, because remember, LCDs do not generate their own light. That light travels forward, hitting a polarizer. Think of the polarizer as a strict bouncer. It only lets light waves vibrating in one specific plane pass through. Then, the light travels through a glass sheet and a set of transparent, negative and positive electrodes. Wedged right there in the middle, between those electrodes, is our star player, the liquid crystal layer. Finally, the light passes through a second glass sheet and a second polarizer before it finally hits your eye to form the image. Let's put this whole system into motion. First, the backlight fires up, producing our raw light. The first polarizer filters it, giving it a strict, uniform orientation. And here is where the brilliant engineering kicks in. When we apply a voltage across those transparent electrodes, we create an electric field. Because our Nematic liquid crystals are highly sensitive to electric fields, they instantly twist their orientation in response. And as they twist, they actually guide that polarized light, twisting it right along with them. So, by simply toggling that voltage on and off, we completely control whether the light perfectly aligns with that final polarizer. If it aligns, boom, light passes through and you get a bright pixel. If it doesn't align, the light is blocked, giving you a dark pixel. The liquid crystals are literally acting as microscopic, high-speed optical shutters. Which brings us to a totally different approach in Section 4, the LED path. Enter the light-emitting diode, the famous LED. This is a total paradigm shift. Instead of controlling existing light with optical shutters, an LED acts as its very own light source. It completely ditches the polarizers and the liquid crystal layers. How? Through the pure magic of semiconductor physics. Fundamentally, an LED is just a PN junction. You have a P-type semiconductor material, which is packed with positive charge carriers that we call holes, and an N-type material, which is overflowing with negatively charged electrons. When you sandwich them together, amazing things happen.
Let's break down exactly how this generates light. Step 1, we apply a forward bias voltage, positive terminal to the P-type, negative to the N-type. This forces the depletion region right in the middle to narrow. Step 2, the electrons from the N-type and the holes from the P-type are driven straight toward that central junction. Step 3, they literally crash into each other. The electrons we combine with the holes. But here's the catch. Electrons in the conduction band have way more energy than the holes in the valence band. So to drop down and successfully recombine, they have to shed all that excess energy. And step 4, that energy is released directly outward as beautiful, glowing photons. It's a continuous stream of recombination, giving us a continuous stream of light. The benefits of doing it this way are absolutely massive. Because we're generating light right there at the atomic level, and because we've totally eliminated the bulky backlights and complex polarizer layers that LCDs need, LEDs give us incredibly high energy efficiency and exceptionally low power consumption. On top of that, they boast lightning-fast switching speeds, a super long operational life, and a highly compact, thin footprint. It's really no surprise that LED technology completely revolutionized not just our screens, but global lighting as a whole. Okay, it's time for Section 5, the LCD versus LED showdown. Let's put these two head-to-head. You'll notice right away how their core underlying philosophies completely dictate their physical properties. Take the LCD setup. Because it constantly relies on a bright backlight shining through liquid shutters, it really struggles to create a true black. A little bit of light always manages to leak through. Because of that, it has moderate contrast, it's also physically thicker due to all those glass plates and polarizer layers, and it draws relatively higher power. Now look at the LED screen. Every single pixel produces its own light. If you want a perfectly black pixel, you literally just turn that pixel off entirely. Bam, infinite contrast. And without the backlight layers, it's significantly thinner, gives you much wider viewing angles, and sips way less power. Let's lock this all in this Section 6, Exam Revision. All right, let's test what we just learned. Here's a classic question straight from the exam bank. Why are nematic liquid crystals widely used in displays? Take just a second and think back to our breakdown of the liquid crystal classifications. What made the nematic phase so mechanically perfect for a screen compared to, say, the Smectic phase or Cholesteric phase?
Okay, here is exactly how you get full marks on this. Your examiner is looking for 3 specific keywords. First, you need to state that the molecules are aligned but free to move, meaning they have directional order but lack strict positional order. Second, explicitly mention that this unique state allows their orientation to easily change under an electric field. And finally, tie it all together by concluding that this results in a fast response time, which is absolutely critical for the rapid pixel switching needed in modern displays. Hit those 3 points and you've nailed it.
Let's do one more. Explain how LCDs and LEDs differ in forming visible images. This is the ultimate test of the 2 display philosophies we've been talking about. If you were sitting in the exam hall right now, how would you clearly articulate the absolute core difference between them in just a sentence or 2? You really want to anchor these mechanisms in your memory. For LCDs, make it crystal clear that they do not generate their own light. Instead, they act as optical shutters, controlling an existing backlight through molecular orientation. For LEDs, forcefully state that they generate their own light directly through continuous electron-hole recombination at a semiconductor junction. Just remember, one is a clever mechanical shutter, and the other is literally a tiny quantum light factory. Before we wrap up this explainer, I want to leave you with a little design challenge to really spark your engineering intuition. If someone tasked you with designing a microscopic 4K display running at 240 frames per second, which technology would you lean towards? How on earth would you manage the heat and power density at that scale? And even cooler, think about what happens to those electrons when we shrink these semiconductor structures down from bulk materials into nanoscale quantum dots. That's a little teaser for our next module. Keep questioning everything, keep